Welcome to the video lecture of Unit 5, MOS capacitor. The subject is Electronic Devices KEC 301. In the previous video, I have discussed about the basic structure of a MOS capacitor, and we have seen that what are the different advantages of MOS capacitor and what is the application of MOS capacitor into a MOS transistor. We have also seen the inversion layer formation, accumulation and depletion into the MOS capacitor. This is the energy band diagram of components that make up a MOS system. In the center we have oxide. On the left side we have metal, that could be any metal, that is aluminum is taken for making the gate layer. On the right hand side we have a semiconductor. In the metal side, the difference between EFM, that is Fermi potential of the metal, and EO is that is 4.1 electron volts. For oxide we have EV and EC difference as 8 around 8 to 9 electron volts, and the difference between EC and EO is 0.95 electrons in volts in case of oxide. For semiconductor, the value lies near about 4.15 electron volts, and the band gap energy of semiconductor is 1.1 electron volts. Strong inversion beyond threshold. Energy band diagram at the strong inversion when Vg is greater than Vt, we can analyze inversion layer which is filled with inversion electron. The inversion charge density is represented with Q INV Coulomb per centimeter square. Phi s does not increase much further beyond 2 phi b, since even a 0.1 volt phi b 0.1 volt further increases in phi s would induce a much larger surface electron density and therefore a large value of Vox that will soak up the Vg. If phi s does not increase, neither will be depletion region width. Approximately speaking, W depletion has reached its maximum value of WD max is equal to under root 2 epsilon s 2 phi b divided by QNA. Now CV characteristics. The capacitance voltage measurement is a powerful and commonly used method of determining the gate oxide thickness, substrate doping concentration, threshold voltage, and flat band voltages. The capacitance voltage curve is usually measured with a CV meter, which applies a DC bias voltage, that is the gate voltage Vg, and a small sinusoidal signal of around 1 kHz to 10 MHz frequency to the MOS capacitor, and measures the capacitive current with an AC ammeter. The capacitance is calculated from using formula I capacitor divided by V of AC is equal to omega C. The capacitance is in the MOS theory is always a small signal capacitance. That can be written as C is equal to dQg divided by dVg equal to minus dQ sub divided by dVg. In this equation, the negative sign arises from the fact that the gate voltage Vg is taken at the top capacitor plate, but Q sub is taken at the bottom capacitor plate, that is the body side. Q sub is the that substrate charge. In the accumulation region, the MOS capacitor is just a simple capacitor with capacitance COX The MOS capacitor consists of two capacitors in series, the oxide capacitor COX and the depletion layer capacitor C depletion. Under the AC small signal voltage, W depletion expands and contracts slightly at the AC frequency. Therefore, the AC charge appears at the bottom of depletion layer. The MOS capacitor, that is C oxide, that is the simpler capacitor, is shown in the figure A, and the figure B is showing the depletion region, the MOS capacitor, depletion region capacitance, and in figure C, it is shown that the inversion layer exists at the Si-SiO2 interface in response to the AC signal. Q inversion increases and decreases at the AC frequency. The inversion layer plays the role of bottom electrode of the capacitor. Therefore, capacitance C reverts to C oxide in the inversion region. The CV curve is called we can have sometimes called as quasi-static CV curve because Q inversion can respond to the AC signal as if the frequency were infinitely low, that is a static case. That would require a ready source of electrons which can be provided by the N region as shown in figure C. PN junctions are always present in a MOS transistor. Therefore, the MOS transistor CV characteristics at all frequencies follow the same curve. What if the PN junction in the figure D is not present? The p-type substrate is an inefficient supplier of electrons. It produces electrons through thermal at a very slow rate for the same region. The diode reverse negative current is small. Q inversion cannot be responded to the AC signal and remains constant at its DC value. Instead, the AC signal causes phi s to oscillate around 2 phi b. The change of W depletion can respond at very high frequencies because it only involves the movement of boundary majority carriers. Consequently, the AC charge exists at the bottom of the depletion region. The result is a saturation of capacitance as Vt at the lower side of the curve. So the curve this is known as CV or the high frequency MOS capacitor CV, HFCV. The name uh, that in the principle at a sufficiently low frequency, even the MOS capacitor CV would follow the upper curve. Following that reasoning, the upper curve is also known as low frequency CV, that capacitance voltage curve. In reality, even at low frequencies such as 1 kHz, the CV of modern high quality MOS capacitor does not follow the LFCV curve. Even then, at lower frequencies, the CV meter is ineffective. The capacitive current is too low. So, for studying the MOS capacitor, the term low frequency CV has an historical significance and it is still being used, but it is no longer has a practical significance. So far we have implicitly assumed that the inversion charge is a sheet charge at the Si-SiO2 interface, that is the inversion layer is infinitely thin. In reality, the inversion charge profile is determined by the solution of the Schrodinger equation and the Poisson's equations. For this reason, the present that it is referred to as quantum mechanical effect in the MOS devices. An example of the charge profile we can take the average location on the centroid of the inversion charge below the Si-SiO2 interface is called as inversion layer thickness T inversion. The average field in the inversion layer can be represented as Vt plus Vt divided by 6 T oxide. It is reasonable that T inversion is a function of average field and therefore a function of Vt plus Vt divided by T oxide can be taken. The electron inversion layer is thinner than the hole inversion layer because the electron effective mass is smaller. It is valid to think that the bottom electron of the MOS capacitor is not exactly at the Si-SiO2 interface. The capacitance rises smoothly towards the oxide because the inversion charge is not located exactly at the silicon oxide interface, but at some depth that varies with Vg. At larger Vg, C poly cannot be assumed to be infinite and C drops. T inversion and W D poly used to be negligible, then oxide thickness T oxide was larger than T, that is greater than 10 nanometer. For thinner oxide they are not, because it is difficult to separate T oxide and T inversion and WD poly by measurement, and electrical oxide thickness T oxide E is often used to characterize the total effective oxide thickness. T oxide E is deduced from the inversion region capacitance measured at Vg is equal to VDD. One may think of T oxide E as an effective oxide thickness corresponding to an effective gate capacitance C oxide, T oxide, and the sum of three other values. Now coming to the MOSFET, that is metal oxide semiconductor field effect transistor. The structure shown is the structure of MOSFET. It is the physical structure of an N-channel enhancement type MOSFET. So here we have, you can see we have a substrate here, and in that substrate we have P type of substrate is there. Into this P type of substrate we have N plus dopings. So one N plus doping is named as source, another is named as drain. At the top of this P-type substrate, we have an oxide layer in this middle, and above this oxide layer, a metal layer, or as we have seen during the study of MOS capacitor, that we can have a metal gate or we can have a polysilicon gate due to its advantage or its stability for the temperatures. So this is the cross-sectional view of the MOS transistor, in which we have P-type substrate at N plus heavily doped N plus region is there, that is named as source, another N plus heavily doped region that is named as drain, and we have a substrate of P type. So this is an N channel enhancement type MOSFET. So it is a 4-terminal device. The 3 terminals are source, gate, and drain, and the 4th terminal is from the substrate one. So MOS transistor is a 4-terminal device. So in MOS we have two type of MOS transistors: N-channel MOS and P-channel MOS. And if we talk about the classification based on their fabrication structure, then we have enhancement type MOS and depletion type MOS. Under the enhancement type MOS, we have two categories: N-channel enhancement type MOS and P-channel enhancement type MOS. And similarly, in depletion type MOS, we have N-channel depletion type MOS and P-channel depletion type MOS. So there are total 4 categories, 4 classifications of the MOS transistor, namely N-channel enhancement type MOS, N-channel depletion type MOS. Then we have P-channel enhancement type MOS and P-channel depletion type MOSFET. So this figure is representing the circuit symbols for N-channel and P-channel enhancement type MOSFETs. The first 3 are representing N-channel MOSFET. The next 3 are representing the P-channel MOSFET. The N-channel MOSFET, here we can see that so the first symbol, that is a four terminal symbol, the second one is simplified one, second and third. In the first terminal symbol we can see there are four terminals: source, gate, drain and the fourth terminal body. In the second terminal the source has been represented by marking the arrow, and here the fourth terminal is not represented. And the third one also, the source is not represented. In the PMOS, what is the difference in the representation of PMOS and NMOS? If we have represented the four terminals, then body of the NMOS will be pointed inwards and the body of PMOS will be pointing outwards. Similarly, if we talk about the simplified structure, then at the source terminal, the arrow will be outward for the N-channel MOS, and for the P-channel MOS, the arrow will be inwards. And in the third representation, in the simplified representation where we have only represented the three terminals, so how we can differentiate PMOS and NMOS? In PMOS we have this small bubble. That bubble is not present in the NMOS. So these are the three representations of the NMOS transistors and PMOS transistors. Formation or depletion region in an N-channel enhancement type MOS. Now we will see that how a MOS transistor will behave if we bias it externally. So here, as we have seen during the study of the capacitance voltage, MOS capacitor, we have seen that what is the effect upon the charge carriers when we apply the gate voltage to the MOS transistor. So we have seen that if we apply a negative gate voltage into the MOS capacitor, so if you see this structure, of this area, then this is simply a MOS capacitor. So if you recall that MOS capacitor, what we have seen that into the MOS capacitor, when we apply a negative voltage at the gate terminal, so that negative voltage will repel the majority charge carriers. Majority charge carriers of the substrates are the holes. So this negative charge will repel the holes from the surface, and here a depletion region will be created near the surface. Here on the drain, the voltage applied is 0 volts, and the source also the voltage applied is 0 volts, and on the gate we have applied a negative voltage. So applying the negative voltage, it is the threshold voltage, the gate voltage is less than the threshold voltage. So if it is less than the threshold voltage, it could have some positive value. For NMOS, the threshold voltage is positive. So if the VG is less than the threshold voltage, means the voltage applied at the gate terminal is not sufficient to turn the device on. Now what happens when we apply a gate voltage greater than the threshold voltage? Then this threshold voltage, what it will do? It will positive gate voltage, it will attract the negative charges from the p-type substrate, and there will be a that in negative charges will be collected near the silicon oxide SiO2 interface. So what happens? It is written here as inversion layer channel. So why it is called as inversion layer? That the surface that was supposed to be of filled with the majority charge carrier holes is now having the negative charges as majority charge carriers. So now it is called as that surface has inverted its state from positive to negative. So when we apply a gate voltage greater than the threshold voltage, the surface inversion is there. And we can see that now even also we have source voltage as 0 and drain voltage as 0. So now we have applied a gate voltage greater than threshold voltage. It has created the inversion layer, but there will be no flow of charge carriers because at both the ends, that source and drain, we have applied the same potential 0. So now we will see that what will be the effect of applying some voltage at the drain terminal. Because here we can see there is formation of charges. Charges are collected here, but on the left hand side on source we have zero voltage, on drain we have zero voltage. So both sides have same polarity, same state of voltage, same amount of voltage is applied. So there is no potential difference. So there will be no flow of charge carriers, and without any flow of charge carrier we cannot expect any current into the circuit. What is threshold voltage? Threshold voltage can be defined as Vt equal to Vt naught plus gamma under root mod of minus 2 phi f plus Vsb minus under root 2 phi f, where this gamma is the substrate bias body effect coefficient. Gamma is equal to under root 2 q Na Xi of Si divided by Cox. Phi f is Fermi level potential and Vt naught is the threshold voltage when Vsb is 0. So what is substrate bias effect or body effect? Normally into the MOS structure we consider that the body terminal of the MOS and the body terminal and the source terminal of the MOS are tied together. Means we have the value of voltage VSB as 0. So here in this equation, if you see this VSB is 0, then the VT becomes independent of VSB. So normally what we consider that VSB is 0 and my threshold voltage is not varying with the substrate to bias voltage. The threshold voltage is not dependent upon the substrate to bias voltage because it is not varying, it is always 0. But when the threshold voltage starts varying with the substrate bias voltage, we call it a body effect or when the source and body are not tied together. The source is at some body is at some other potential, then what will happen? There will we have some value of this VSB, then the threshold voltage will vary according to the variation of VSB and the threshold becomes variable with the substrate bias voltage. The variation of this threshold voltage with the VSB is called as substrate bias effect and gamma is called as the body effect coefficient. Now these are the symbols that are representing the another kind of the MOS, that is circuit symbol of N-channel depletion type MOSFET. First here the difference between the previous one, we can see that this side is made broader. So if this side is off towards the gate is made broader, means it is representing a depletion type MOSFET. So in depletion type MOSFET, the channel is already there during the fabrication process. So this broader side is representing the already formed channel during the fabrication process. Now we will see that how the MOS will operate when we apply some external voltage. In the previous one we have seen that we had applied gate voltage, but the source voltage and the drain voltage was kept at 0. So there was an inversion layer formation, but no flow of charge was there, so no current was flowing there. Now here in the figure A you can see that at the drain terminal a positive voltage is applied. So what will be the effect of this positive voltage? Due to the effect of this positive voltage, the depletion region towards the drain will get broader and the channel will get thinner towards this um, towards the drain. Why this will happen? Because here Vs minus Vg will have some larger positive value, so that positive value will attract more negative charges. If you look in the right half of this circuit, then there will be a small difference between Vg and Vd, so that due to that effect a small voltage will be applied to this region and the charge attracted near the interface will be reduced. So the channel will get thinner towards the drain side and the depletion region will get broader towards the drain side. Now applying the positive voltage towards the drain side will attract attract the negative charges of the channel towards itself. So when the charges will be attracted towards it, there will be a flow of charge carrier from source to drain, and a current will start flowing from drain to source. The further working I will discuss in next video.